All right, so let us continue talking about word embeddings. And this week we will talk about extensions of the basic paradigm that we have seen, not in the last lecture, but in the lecture before the last lecture. And in particular, we will talk about syntactic word embeddings, or more syntactically oriented word embeddings, about bilingual and multilingual word embeddings, where where words of several languages reside in the same vector space. And then, of course, all throughout this lecture, we'll talk about the more recent contextualized embeddings. So, what we have seen in one before the last lecture was that word embeddings can represent semantic and syntactic relations between words in a vector space. So, here what we see is, well, these are like semantic analogy relations that we see here, like the vector that combines man and woman, or the man and woman are situated in such a way in the vector space that their difference is the same as the difference between uncle and aunt and king and queen. And also, we have also seen that embeddings can capture like more grammatical aspects also. So the difference between kings and king is analogous to the difference between queens and queen, and is S here in both cases is the plural marker. So this would be capturing more of a grammatical aspect. So in this lecture today, we will talk about, as I've already outlined, multilingual, multisense word embedding. So multilingual is you have multiple languages in the same vector space. Multisense is you attribute each sense of the word a different vector. So that's actually an old idea, and but has only more recently become very influential with the advent of Bird and Elmo, i.e. contextualized word embeddings. Afterwards, we'll talk about getting word embeddings that still capture semantic, but also capture more aspects of grammaticality or syntax. And then finally, we'll conclude with a couple of different things, including talking more about contextualized word embeddings. So what is this picture here? On the right side, this is a picture that shows like a genetic evolution of organisms or animals, starting from some base organism that then develops into very different categories. And well, we could actually sketch a similar evolution for word embeddings also, because they were a very popular, very important topic. So many people worked on that, and developed more and more different branches of word embeddings, like those varieties that we will also, or some of those varieties will also be discussed in this lecture today. So the first thing that is we start out with is word senses. So what we know is that words do not only represent one meaning, and we have an example here. So here are three objects, and these objects in English can be denoted by the one and the same word, and this word is a table. So here here's the first table. That is a synonym of that is maybe desk. Then we have another table here that's like a mathematical table, where you can insert figures in the table, and that's a piece of chocolate, and this also called table. So we have one word, and it has different meanings, it has different senses. And this is a pretty common phenomenon in most languages, especially also in English, where we have the case that verbs and nouns can often have the very same form, but we also see here an example where even a adjective has the same form as a verb and a noun. And in this case, we have the fly. This is a noun. We have to fly. This is a verb, and we have an adjective uh, that also goes by the word fly. This is the same word form, but different meanings, different senses, right? This one word has different senses. So the problem is generally known as polysemy uh, and homonymy. So a word may have different meanings, as we have just seen. The difference between polysemy and homonymy is polysemy is the case where a word has different meanings that are all related to each other. For example, well, at least fly and to fly. These are obviously quite related to each other, but there are also cases where there's absolutely no relation at all. One of these cases we've already seen. The modal verb can and the noun can are probably not related at all, not even historically. And the same is probably true of fly and of the adjective fly and these two meanings here. So homonymy is a case where the different senses are not related to each other. Okay, but in general, we see for almost all words such either polysemy or homonymy. If you go to some lexicon, you look up words like man, you find entries 1, 2, 3, which all represent different senses of this word. Mole, bank has 3 different senses in this lexicon at least. Book has several different senses in this lexicon. So if you go to any lexicon, you typically find more than one sense for each word. So, and this is of course a problem for our classical approach that we learned last week, word to vec, because that assumed that each word has exactly one representation, and this representation cannot differentiate different senses, right? So no matter which fly you have, you would always get the same representation of fly. So what were people doing to address this back in the bad old days, like let's say 2014, 2015 around? So there were a couple of papers trying to address that. One of these papers was doing something like the following. They had a sense disambiguated corpus where there was text like, let's say, a rush of panic called Sarah. So this is one sentence, but in this corpus, obviously, there are several thousand or hundreds of thousands of sentences in this corpus. They are annotated by humans. They have been annotated. So pause is the part of speech. So this is a determiner. This is a noun. This is it's probably some kind of particle, and called is a verb, for example. So we have part of speech information, we have lemma information. So what is the base form for called? It's catch. And we also have this word sense information, right? Where it says, okay, this is the second word sense of rush, this is the first word sense of panic, and this is the 12th word sense of catch. Okay? So we have this word sense information. Where do we get this word sense information from? Well, we could get it from humans. Humans could have labeled such texts by saying, okay, so they go over each word or each sentence, and then humans say, okay, this is the 12th sense, this is the 4th sense, etc. And what do they refer to? Probably they refer to some database or some lexical resource that collects words, that informs how many word senses there are for any given word, right? And one such lexical resource is, for example, that's for example not Wiktionary, but or maybe also Wiktionary could be, but in particular WordNet. So WordNet is such a resource. If you've heard that. So WordNet gives many different lexical semantic relations in English between words. For example, which word is related to another word, and how many senses the words have, etc. And then if we ignore all other information except for the word senses and the plain text, we'd have a rush of panic codes error, and then we'd have the word senses down here. Okay, so we can train on such a resource with different word senses labeled, and we do that. And then, for example, here we see bank. That's a noun. The upper script symbol denotes the word class. So we have a couple of nouns here. We have the different word senses. Bank. One is the geographical, the bank of the river, and then we have the financial bank. And for number, maybe there are also different word senses, or you can have a telephone number, or that you can make a great number in some TV performance. And then, like, okay, so our words have different senses, and now we learn the representations on such a corpus, right? Now we have the index, so each sense gets a different embedding. And then we can query for the nearest neighbor, and you see that, well, okay, at least some results are intuitive, right? So because, well, the nearest neighbors of bank here, the one which had the signification of the bank of the river has like upstream, downstream, runs, river, stream, etc. And the financial bank has like commercial bank, savings bank, banking, etc. So okay, so that seems to make sense. Now, what is the main problem? What is the main problem? Well, the main problem, of course, is we need to have such a lexical resource, and it has to be have been annotated by humans, which is a very costly thing, right? So that can be very, very costly to have, and for most languages, such a thing does not exist. And then the second question is, how do we train an NLP system with these sense disambiguated embeddings? So what is the problem that we are facing? The problem that we are facing is, now if we get in a new word like bank, we'll have to know whether this, and we feed that into some system, which then makes a prediction based on this, based on the word and the representations of this word. Then of course we need to know, is it a river bank or is it a finance institution? So we would have to solve this problem, we would have to train another system that is doing this word sense disambiguation. So this task is called word sense disambiguation. And this second system would have to run word sense disambiguation for us. And then when word sense disambiguation has been performed, we could feed in for each sense of the word our word embedding, and then run our NLP system that is solving any task, like named entity recognition or part of speech tagging or whatever. Good. How could we do it differently without having having to have access to such a lexical resource? What we could do is more parsimoniously and unsupervisedly. So in this previous approach, we had supervision. How could we do it unsupervisedly? Well, we could first run word2vec on our data, and then we compute embeddings, right? And then let's say we have target word like bank. We take all the contexts of this target word. So we look over all the occurrences of bank, and we look to the left and to the right of the word. For example, we could have a sentence like need to go to the bank to get some money, or the raw water is largely riverbank filtrate, or runs from its idyllic riverbank promenade under the Elbe to, etc. So these could be our contexts. Our sentences that all include the target word that we're interested in. So now we look at the context. Let's say we define the context as the 4 words to the left and the 4 words to the right. So that's how we would characterize the context, the immediate context of a word. And we could we could represent these contexts like as the average embeddings, right? So we have an embedding here. That's what we got from word2vec. We have an embedding here and here and here and here. For all of these words, we have embeddings. We can average them, so we get a context representation, right? So here another context representation, here another context representation. So we would get, if we have thousands of occurrences of bank, we would have 1,000 vectors, context vectors, for each instance of bank. Now what we can do next is we cluster these context representation using some clustering algorithm, and you've seen in the lecture on machine learning at least the basic principles of clustering. So basically you have a high dimensional space with points in that space, and you want to unsupervisedly group those points into different categories. So you say, okay, here's a group of points that belong together, and here's another group of points that belong together. And you can use such a clustering algorithm such as k-means, and you assign each word's context to a cluster. So you would say, okay, these two here, maybe ideally, so intuitively, these two would have the same cluster index, and these two. And when we say these two, we actually mean those context vectors, right? So those two would go in one cluster ideally and intuitively, and these two would go in a different cluster. And then once we've done that, we can again assign this bank here as bank number 1 and this bank here as bank number 2. And then we could again, now that we have sense disambiguated our bank, we could run word2vec on this sense disambiguated corpus and get vector representations for each sense of the word. And of course we would have to do that with all the words in our vocabulary. I mean, this would be pretty expensive, but in principle this is an approach that could be done. And again, to tell you what is clustering, as I said, we have in general, clustering is we have points in a high dimensional space. In this case it's just 2-dimensional, and our clustering algorithm would tell us here's a group of points that belong together, here's another group of points that belong together. And depending on how the clustering algorithm is implemented, well, the clusters could look differently, and the form of clustering that is a result of the clustering algorithm could look differently, but in principle we would hope that there are a couple of clustering algorithms out there that give results that correspond to our intuition of the data. Good. So this was back then in 2014, 2015, and some people came up with these approaches of using sense embeddings, but there was not so much benefit in general in using them in practical applications. And on the other hand, there was a high cost involved, namely you needed this sense labeler, or maybe you needed a more complicated model, so people did not use that. So there was little benefit and high cost, so people said, okay, let's not use that, let's just use plain word2vec. But then in 2018, Elmo and Bert came around, and they actually are a different implementation of the same idea. They also give contextualized word embeddings. So depending on the context, you get a different embedding for each word. So if you see bank in the context of river, you would get a different embedding for bank than when you see bank in the context of Deutsche Bank, for example. Okay? Or in the context of money, right? Then you would get a different embedding for bank. But so that's the same idea, but the approaches to obtain these contextualized embeddings here are actually quite different. They are much more parsimonious and more elegant, and well, they do not require any human annotated resources, for example. Even though they are also very costly, but the cost is actually mostly in obtaining them once, and once you have the models, you can get the vector representations relatively cheap. Okay, so this was multi-sense embeddings. Now let's go to bilingual embeddings. So what are bilingual embeddings? So the idea is so first, what are monolingual embeddings? So these are the embeddings that we already know. Monolingual embeddings is you have a vector space where you represent all the points in your vocabulary in the vector space with vectors, and you hope that the vector space has the property that semantically similar words like bike and car, eat and drink, man, woman, and child are next to each other, and maybe also some grammatical relationships are encoded. But basically, we would first hope like that semantic is properly encoded. And of course, we could have such a space for different languages, like German. We could have a similar space. And then the goal in for bilingual word embeddings is we should have one shared space with a shared feature space where all the points from both languages are, but in such a way that also cross-lingually similar words are close to each other, like essen and drink. So these are not words from the same language. One is German, one is English, but they are close to each other. So this is the basic principle of bilingual word embeddings. And as you can already see from this example here, what does not work is that you just you take one vector space, you take another vector space, and you put all the points straightly in the same vector space. So you cannot just plug Feuer up here and Licht up here, because in this case you would not get the property that cross-lingually similar words are close to each other. And the reason is that this approach does not work is because all of these vector spaces, well, they have the property that the nearest neighbors of a word should be stable. If you run, for example, the algorithm twice, let's say you run word2vec twice, then you would hope that you get the same nearest neighbors, but you would not get the same location in general, right? So at one time, if you run word2vec twice, Oma, Opa, Vater, they could be like metaphorically speaking, they could be here upright, and the second time they could be down here, and this is totally plausible. But you would hope that they would still be together. So what does not hold is that their location would be preserved, but probably their neighborhood would be preserved. And from this, you can already infer, even if you run English or German twice, and you plug the words together, then from both runs, then you would not get any meaningful results, because the words would be in totally different locations. And if that is already not true for one and the same language, then the more it is not true for two different languages. So just like putting the points all in the same vector space without any operation, without any mathematical operation, does not make sense. Good. And as I've already said, we can think of this bilingual embedding space consisting of two objectives. One is a cross-lingual objective. Words that are translations of each other should be close in the shared space, and the monolingual objective is the same as in the standard word2vec, namely words that occur in monolingually similar contexts should be close to each other in the word space, in the vector space. So if two words have the same context, then they are supposed to be semantically similar, and therefore they should be close in the vector space. So we can think of the bilingual vector space having these two objectives. Why do we want to have bilinguality? So what is the motivation? So in the first papers, people said, okay, the second language may act as an additional signal, which may help to improve the word embeddings even in the first language. So one motivation could be to make the monolingual word embeddings better. So that's why we need a bilingual space. And to make an illustration, let's assume that the word like Opa occurs very infrequently in the German corpus, maybe because the German corpus is also very small. And therefore, because it occurs very rarely, let's say only 2 or 3 times, you have small statistics, you have a case of small data and small statistics and unreliable statistics, so to speak. And therefore, the vector of OPA cannot be reliably estimated. Maybe it's entirely falsely estimated. Now, assume that, however, the English translation grandfather occurs quite frequently in the English corpus, maybe because the English corpus is 100 times larger. Then we can get a good estimate of grandfather, and then if the mapping is good, so if OPA can indeed be mapped to grandfather in the bilingual space, then we would hope that all of a sudden OPA gets a good representation in the sense that the nearest neighbors of OPA are like close to what they should be, or at least much closer to what they should be than they were when you only had the small German corpus. So this is one motivation, how you can motivate them. It doesn't mean that this motivation is correct in all cases. It could also mean it could also happen that it gets a little better for the one language and it gets a little bit worse for the other language. That's also possible, but in principle, this is one thing, one motivation that you could bring forward to defend bilingual vector spaces. Now, a second one is to perform something that has previously been called direct transfer, and that would probably today be called as zero-shot learning or zero-shot transfer. And what is that? So the idea is, if the words are in a common space, so you have shared features, so each word has an embedding, and this embedding can be considered as like a feature representation of the word. And now if you have words from different languages in one space, then you can train the model. You can train a model in one language, which would usually be English, because you have a lot of data in English. So we could train some NLP classifier, let's say a part of speech tagger in English, for which we also have labels. And then we could directly apply our part of speech tagger in German, for example, if we have a bilingual space, but we don't have any part of speech labels in German. So that's actually a very cool application scenario. And to phrase that out again, to illustrate this with an example, so consider indeed the task of part of speech tagging. So let's assume our training data has the form of English sentences and their part of speeches, like I may not drink this, then the I is a pronoun, may is a verb, not is a particle, drink is a verb, this is a determiner. So you have labels, but in the end you want to apply this to German, for which you don't have any labels, or like to Swahili, you name the language that you want, for which you have absolutely no labeled data. What can we do? So first we need to come up with an architecture. Let's say, which architecture could we choose? Well, we could say we take all, so up to now we mostly know MLPs. We don't know recurrent neural networks yet. So we try an approach with an MLP. For example, if you want to label the word drink as a verb, we could take the one word to the left and one word to the right of drink as a representation. Then we convert that representation into vectors. So we get a vector here, we get a vector here, we get a vector here. Where do we take these vectors from? We take them from our bilingual space. So the drink would get this vector here, not would get some other vector in this space, and this would get another vector in our space. And then we train a classifier on that. And of course it has a softmax output, the network that we would train to do multi-class classification. We would predict that this is a verb. So this occurs in the training. And then at test time, so we train using the bilingual embeddings, but of course the English part, and assume we have a big English label data set. And then afterwards come in German words. and they also get representations, but those representations are close to the English representations. So if afterwards the German word trinken comes in, then trinken has a vector representation that, as you see here illustrated in the graphic, is quite close to the English vector representation of the word drink. Okay, so this is let's say that's a better motivation of bilingual vector spaces. And what are problems with this direct transfer approach? So one problem is the syntactic ordering. So different languages have different syntax. So for example, in German, you can put the verb at the end of a sentence. And in English, you usually cannot do that. And if you only train on English data, then you would probably expect that your classifier, if it has been applied, if it has been trained on English, would not perform so well for the German data. And the other thing is that all words in the test data are what we would call out of vocabulary. So that means they have not been seen during training. And why have they not been seen during training? Because you have seen drink, but you have not seen trinken during training. And you see that trinken is a little bit off, right? It's not very much off, but at least it's a little bit off. And this has the potential to again confuse the classifier, and therefore you would also again expect that there is a performance drop when applying this classifier to another language. But still, in general, you could assume that the drop is not very dramatic, depending on the quality of the bilingual vector space and depending on the similarity of the languages.